Well, the last thing we went over just before your extended spring break was the thick lens formula, and since that was a number of weeks ago, let's review that here, and then we'll launch into working some example problems. So, just for a quick review, that's the diagram that you should have somewhere in your notes that we went over with last time. Remember, we have a thick lens here, index of refraction n, and in front of it we have a media n1, index of refraction, and behind it a media with the index of refraction n2. And the purpose of these thick lens formula are to locate the primary and secondary focal points f1 and f2. And we actually did it for just the back focal length. That was the way that we attacked it. And a couple of things to note. The thickness of the lens is the central thickness, so there's the optical axis, so that's the distance between the front and the back of the lens along the optical axis. We've got two principal planes to H1, H2, and H1. We have script F2, I called it, which is the back focal length that's measured from the back vertex to wherever the secondary focal point is. We have the focal length F2 that's measured from the secondary principal plane H2 horizontally. And our sign convention is any vector pointing to the right is positive, any vector pointing to the left is negative. And we have similar things on the front side. It's convenient to define the refractive power, and we've seen this before, of the curved surfaces at the front and the back. And so P1 is the refractive power at the front surface, and that's n minus n1 over r1. And P2 is the refractive power of the back surface, n2 minus n1 over r2. And we went through basically some basic geometry and a few relationships to find the following formula there for the focal length F2 from that secondary principal plane H did H2. In terms of P1 and P2. So usually in these calculations, what I do is, as we'll see a little later, we calculate P1, just P2, just automatically, assuming we know all of those things, which in any design work you would. And then thickness is always a positive quantity, so it's the central thickness. And one can, assuming you know N1, N2, R1, R2, and can measure the thickness of the lens, then you can use this to get that focal length f2. One, you also can use that to get that BF FL, back focal length. Remember, it's measured from the vertex here, the back vertex, and so once I've got f2, I can plug that in here and get script f2. And then if I want this distance h2, I'm not sure I wrote this equation down before break, but it's generally convenient to have two. Pretty obviously, if I have f2 is positive and script f2 is positive and f2 is positive, then h2, if I define it to be f2 minus script f2 minus f2, is going to be a negative, and that indicates it's moving. It's would be in that direction toward the negative. So these we derived in some detail, not hard, but kind of tedious to go through it. And then to get the second half of the equations, really all you have to do is interchange f1 and f2 and honor your sign convention. What a lot of people do is assume that you've got parallel light coming in from the right to the left and go through exactly the same calculations that we did before. Anyway, you're encouraged to do that, but I won't go through it. I'll just tell you the results. This formula here for the back focal lengths really doesn't change on this side. If I interchange P1 and P2 and substitute two for one for two here, I have to honor their sign convention that it would be toward the left. So that I put in by hand really this negative sign in this method. But if you derive the problem and honor your sign conventions, that's what you'll come out with. And then once I solve this for F1, then I can again just interchanging twos for ones and ones for twos. This equation up here transforms into this one. Interchanging twos go to ones, I get this result here. And we have our complete set both for both sides. Um, Note if I look at this equation up here for F2 and the one for F1, that the right-hand sides are identical on both of those because they're symmetric under the interchange of one and two interchanges. And as a result, they're both equal to the same thing, and so minus n1 over f1 has got to be equal to n2 over f2. And so usually people don't necessarily use this second equation. They simply use, once they've calculated f2, they can use this to find f1. And then once they've found f1, you can find script f1 from this formula, and then get h1. Another thing to note that most of the time you're in air, or really you might not be in air, maybe you're in underwater or something, but usually n1 is equal to n2, and if it is, those will cancel out, and you get f1 is equal to minus f2, the negative sign again because it is from the picture above, it's going in that opposite direction toward the negative x direction. So that's the most common case that we'll see. Well, that's a quick review, and we'll launch into the next video to using this set to work some equations. So make sure you copy these down on a piece of paper, and then we'll come back and use them for the next couple of videos anyhow.